We are very happy to have Simon from Cardiff who will tell us about going beyond rigidity. That's all.
Thank you very much, Rudy. And yeah, thank you very much to the organizer for this opportunity to speak and inviting me to this very significant conference in a beautiful location. So, in a way, the organizers have done an excellent job with scheduling, with putting my talk right after hazards, which featured rigidity quite heavily, and now we're going beyond it. And so I split the talk into 3 parts. So I want to talk a little bit about monoidal categories or tensor categories and dualities. This is where rigidity comes in to sort of set the context. Then we'll be talking about something called module categories, which I'll explain when we get to it, and then results. So I'm trying to keep it simple. And so just briefly, yes, just recalling rigidity. So as I explained in more details, and I just want to go over some of its aspects. So if you have a monoidal category or a tensor category, then an object that means a rigid may or may not mean a rigid dual, which is another object, C with a check on it, that comes with 2 morphisms that satisfy certain relations called zigzag relations. And if you can't remember them, it's not important because they won't show up again. The important thing to remember is just there's these 2 morphisms that satisfy 2 equations. And because you put the dual object as the one side of the object C, you can also do it the other way around, and that's the opposite type of duality that comes in the hand. This is a left dual, but it's right duals. And then we call an object rigid if it allows both a left dual and a right dual. And the existence of duals is a property rather than structure. And by that I mean if they exist, they're unique, so there's no choice. And with structure, I like to think of having choices. So examples of rigid structures. The easiest one is just finite dimensional vector spaces with their tensor product. And there the notion of taking a dual is literally just the dual vector space. A more sophisticated example is the category of finite dimensional modules over a finite dimensional Hopf algebra. So this escalated pretty quickly, but this is another good source of rigid tensor categories. And so rigidity has many nice consequences. If your category is abelian, then the tensor product functor is exact in both eigens, as I mentioned that earlier today. Projective objects form a monoidal ideal, which was a central point of that score. And taking duals is off-monoidal, so it preserves the tensor product, but it reverses the order of the tensor product. And my take on this is actually extremely restrictive in the wild. This is generically nature is not like this. Examples for this, if you take a category of finite dimensional, so if you take a finite dimensional associative algebra and consider its bimodules, then the tensor product of bimodules is generally only right exact, but it very much need not be left exact. And then sort of my own home territory, vertex operator algebras. If you take a vertex operator algebra and consider a category of modules and apply some mild sanity conditions, these sanity conditions are just there to make sure the tensor product exists. But then if it exists, it is generally only right exact. And if being left exact and giving you a modular tensor category or something like that is very strong and extremely restrictive. Vertex algebras won't really appear much more other than that this is the source of examples that I draw my inspiration from, that we're going to be talking mostly about categories today. Yes, and so just to illustrate this a little bit more, to keep things concrete. So if you have an algebra A and 2 bimodules B and B twiddle, the way you construct the tensor product is via a co-equalizer, right? So the 2 double arrows, if you've got B tensor A tensor B, you can either use the action from A on the factor on the left, or you could use the action of A on the factor on the right. And this double arrow just means you take the difference of these 2 actions. And then the kernel of that is you mod out by the difference of these things, and that gives you the tensor product. And so this is why it's roughly the same. But there's more to the story. So if you have a bimodule, you can also consider it linear dual, B star. And this is also naturally a bimodule, where now the action on the linear function of beta is obtained by taking into the argument but swapping the sides. So you just reverse the sides. This turns every dual space also into a bimodule. In particular, the dual of the algebra is also a bimodule. And what we'll see is, so I mentioned the top, I wrote at the top, that's what I said, but the monoidal unit, so the identity element for this tensor product, is just the algebra itself. And when one has rigidity and looks at these modular tensor categories, one generally wants the tensor unit to be dual to itself. And for algebras, this need not be true. So the dual of an algebra need not be isomorphic to itself as a bimodule. And I've given a small example here. Consider the polynomial algebra in two variables and mod out by x squared, y squared, and xy. That's a three-dimensional algebra. It has a unique simple module. Basically, you get that by setting all of the variables to 0. And if you try and decompose it, you see you've got a two-dimensional simple submodule, two copies of the simple module, and quotient by that is isomorphic to the simple module. So if you go and dualize this, you of course reverse all the arrows, and you get a completely different exact sequence, and hence A star cannot be isomorphic to A. And so, yeah, so this is hardly a particularly far-fetched example in a sense, and so we'd like to have a duality structure that can accommodate these kinds of properties. And we can go a little deeper. So the dual of A might not be an algebra, but it is naturally a co-algebra, and it allows us to actually turn any A bimodule into a bi-co-module. And we do this in a surprisingly trivial way. So if you've got an element B in your bimodule, instead of acting on it from the right with the algebra A, we can decide to just not act on it and leave that slot open. And then we've now gotten something that's got an element in B to an element in B tensor functions on A. And the same on the left, and this actually turns it into a co-module. And for co-modules, we also have a tensor product. But now it's constructed through an equalizer rather than a co-equalizer. So we can get and I've written it down there, and there the double arrows are just the difference of the two coactions. And so we get this cotensor product, and its monoidal unit is the dual of A. And interestingly, there's sort of duals and tensor products are nicely interrelated, where we have the tensor product of two bimodules B and B twiddle going into the dual of A. These Hom spaces can canonically be identified with algebra module maps from B to B star. That actually should be a wavy equals. They're not literally equals, of course. And an object in a tensor category satisfying this property that we've written here. This is a dualizing object, and that will appear later on again. And this, yeah, as I said, this tensor product of co-modules is naturally left exact. And so what you'll see throughout this talk is we'll always have one version of stuff which tensor product which is maybe more familiar, which tends to be right exact, but then there's always a way of just reversing things around, and then you get the other thing. And one of the central conclusions of this talk is that we need to treat these structures on an equal footing. And just to revisit the example in the previous slide with this three-dimensional algebra that we had here, you can work out the tensor products, and you see that they're different. So we tend to take the tensor product of A with A, because A is the tensor unit. We don't have to do any thinking here to evaluate this. It's just A. Here, you have to go through and do that calculation, and what we end up with is the cotensor product of A with itself is 4 copies of a simple object. And so they are generally different tensor products. They are both, I would argue, quite active. And so this brings me to the main structure that I want to talk about today. A Grothendieck-Verdier category or a star autonomous category. They had the name star autonomous for a long time in the 70s, and then Voyachenko and Drinfeld in the late 90s decided to call Grothendieck-Verdier. We're going to Grothendieck-Verdier. So let C be a monoidal category. An object K in C is called dualizing if for every object Y in C, that functor there is representable. So we send X to hom of X tensor Y to K. And when I say it's representable, that means we'd like to have some new object GY such that these hom spaces can be canonically identified. So X tensor Y to K can be identified with X going to GY. This defines a functor G, which is contravariant, and we require this functor to be an anti-equivalence. So not only must such a functor G exist, it must also be an anti-equivalence. If these two properties hold, then we call a monoidal category together with the choice dualizing object a Grothendieck-Verdier category. So it's a category that allows, for this whole thing, we call it Grothendieck-Verdier duality. And so this functor G is going to replace the role of taking rigid duals from the rigid example. Okay. And I said more examples, but there's actually more properties, I think. So Voyachenko and Drinfeld showed that the subcategory of dualizing objects is a torsor over the invertible objects. And the important thing to take from this is, unlike rigidity, dualizing objects of Grothendieck-Verdier duality is a structure. So there can be three dimensions. I mean, the course of none, or just one, but yeah, it's whether or not we have invertible objects, basically. Now with the examples, so why I'm interested in this, together with my PhD student, Robert Allen, Simon Lentner, and Christoph Schleiger, we noted that categories of vertex operator algebras, so categories of modules of vertex operator algebras with mild assumptions are Grothendieck-Verdier categories with a distinguished choice of dualizing object, which is the dual of the vertex operator algebra. So there's a distinguished way of taking duals in the context of vertex operator algebras. You basically take a dual vector space, and that is a distinguished choice of dualizing object. And actually, because vertex operator algebras come with way more structure, it's more than just a Grothendieck-Verdier category, it's a ribbon Grothendieck-Verdier category, but we're not going to talk about the ribbon structures today. And my PhD student Rob also showed that Hopf algebroids give yet more examples of Grothendieck-Verdier categories. And of course, the previous example that we had with modules, bimodules over associative algebras is also an example. So I would argue that this is a good duality structure that is representative of many things that you find in nature or in the wild. And so important consequences of the existence of Grothendieck-Verdier duality. So if we have Grothendieck-Verdier category C with dualizing object K, then we have a second tensor product, which I'll denote with like a dark symbol. I like to think of these as ghostones. You've got the white side and the black side, you split them around and each are fine. And so in the associative algebra example, the co-tensor product, so this tensor product of co-modules takes exactly the place of this second tensor product. One property that rigid duals had, that this still also has, is that you can move the tensoring between the sides of a hom space. So the white tensor product has a right adjoint, and these are generally called internal homs. And the specific formula is given there on the right, and it's formulated in terms of the other tensor product. And there we also see that this other tensor product has the black tensor product has the white tensor product as its left adjoint. So left exact. And which is the line below. And so the left adjoint of the black tensor product is called the internal cohom, and the right adjoint of the white tensor product is called the internal hom. And this equality up here should also remind you of something from linear algebra, the hom tensor adjunction, right? So if you've got on the left hand side, if you're thinking of just linear algebra, these are maps from x tensor y to z, but you can just leave out the y in your function that takes two arguments, and suddenly it becomes a map from x into functions from y to z. So this is what this is categorifying. It's just the hom tensor adjunction. And so why do we care about this? Now we're going to go into module categories, and why do we care about those? So the construction of two-dimensional conformally invariant conformal quantum field theories, or CFT, requires module categories. In particular, Frobenius algebras constructed from module categories describe boundary field objects in CFT. So I'm originally a physicist, and I'm hoping that this will allow me to do interesting physics. Then there is also a purely mathematical question within the sort of literature of star autonomous categories or Grothendieck-Verdier categories. Distinguished morphisms called distributors were proposed, which sort of associate the white and the black tensor product, right? They allow you to sort of re-bracket them, but they were very poorly explained and generally loaded with additional assumptions that didn't really seem necessary, like the category being symmetric or something like that. And while I won't go into this in much more detail here, we managed to sort this out and give a canonical construction of them. And so you can sort of associate between the two tensor products in a Grothendieck-Verdier category. And yeah, the bizarre, or the interesting thing is, while these are important, like structure morphisms in the category, normally structure morphisms are isomorphisms. These distributors need not be. I mean, they can actually be the zero morphism. Yes.
I mean, maybe it doesn't make sense, but are they coherent? I mean, they're not isomorphisms. So that's right.
I mean, they're coherent. They're natural transformations, and they satisfy pentagons like the associated. Yes, absolutely. And those, if you want to write it out, there's like, because you have to take into account of where the tensor products, there's like 32 of them rather than just one, which is why we need a good conceptual construction, because we didn't want to verify 32 hexagons. But yes, that's a very good question. Thank you. And so, or back on this. So when we does tensor categories, one often likes to have graphical calculi. And for that, one needs to have like a associativity, or the associativity being trivializable is really important. And this makes having a graphical calculus extremely hard, because these are not isomorphisms. So you can't just, but you can, at least when you're trying to write down conjectures, you can like act as if there's a graphical calculus to formulate what you think must be the right argument. But then you have to actually work with the real coherence diagrams and to do the proof, which is a bit tedious. That's like okay, so what are module categories? So everything I'm presenting now is from the paper that I linked to on the title page. So a left Grothendieck-Verdier module category over a Grothendieck-Verdier category C is a left module category. That means it comes with a action functor triangle, which allows basically to combine an object from C with an object from M to get an object from M. And we want this functor to admit right adjoints when you fix either of the arguments. The right adjoint of keeping an element M fixed, we will call an internal hom. And the right adjoint of keeping an element C fixed, we don't have a special name for it, it's called an R. And an important consequence of this is then that given such a action with right adjoints, then we automatically also have an action with respect to the second tensor product. And so this motivates that why we call these things Grothendieck-Verdier module categories. They are naturally compatible with the Grothendieck-Verdier structure. You don't have to postulate a separate action for the other tensor product and then make them compatible in any way. It's just enough for the action to admit right adjoints.
And there's also no condition about KX.
Sorry?
There's no condition about KX.
There's no condition on how. No, there's no condition on how KX, so K will act as the unit for this black triangle, but that is a consequence of the tensor unit being the unit action on the white triangle. And so all you have to do, so you could alternatively verify the axioms for the black stuff, and then you get the white version. And so that's why it goes to, it's just two sides of the same coin. And so now at this point, we are able to appreciate why I chose this talk for the conference. So we're supposed to have topology, representation theory, and higher structures. The topology one is shaky. This stuff can be used for topological field theory. The higher structures, tensor categories are at very least two categories, so two is greater than one. And for the representation theory there, I think I nailed it, because category C is normally the category of representations of a vertex algebra or some other algebraic structure. And now we're representing these representations. So we've got representation theory squared. So good. And so when you've got such a module category, there are two distinguished subcategories within it, which I'd like to characterize now. So, so we've got our Hom and co-Hom functors, which we got by taking adjoints of the actions where we fix the element that comes from the module category. Then we call an element, an object in the category M, white tensor admissible if the internal Hom functor is a strong module functor. So they're naturally weak module functors, and weak means some of the structure morphisms that come with them are not necessarily invertible. But when they are, then it's a strong module functor. This internal Hom being the right adjoint of something naturally has a left adjoint, but need not have a right adjoint. But if it also admits right adjoints, that's a stronger property. And so the objects that satisfy this, we call them the admissible objects, and they form a subcategory. We can do the same with the black tensor product, again, because everything is completely symmetric. We can always do anything. We can make a statement about one version, we can always make a statement about the other. And we can apply this to the tensor category C, thought of as a module category as well. So we get two distinct subcategories there. And so within the tensor category C, the subcategories are monoidal subcategories, one for one of the tensor products and one for the other tensor product. Generally, this one will always contain the tensor unit for this tensor product, but need not contain the tensor unit for this tensor product, and vice versa, which is why the monoidal category is only for one. And I mean, this also need not be closed under, sorry, this need not be closed under the black tensor product, and this need not be closed under the white tensor product. And then if you do this in the module category M, the white tensor admissible are closed under this subcategory, and the black tensor admissibles are closed under this subcategory. And I mentioned before that we wanted Frobenius algebras, so we're getting towards that, we're at least getting algebras. So for any object M in the module category M, the internal end, so Hom M comma M, is naturally an associative unital algebra in C white tensor. And the internal co-end is naturally a co-associative co-unital co-algebra in C with the black tensor. And we also have a natural sort of functor from M to modules over AN. And so, and the same is true for internal co-homs. This gives us a functor from M to co-modules over CM. And so if you were going to ask you for some natural examples of modular categories, this is working towards it. We can say when these internal Hom functors and internal co-Hom functors are actually equivalences of modular categories. And that is this proposition here. So for an element, an object little m and big M, the internal Hom functor is a modular equivalence if and only if M lies in this distinguished subcategory and M is a C generator of big M. And C generator just basically means acting on that little m with all of C allows you to surject on any object in M. And then similar for co-Hom. And so, okay, so now if you ask me, could you please give me examples of module categories? The first trivial example is just the monoidal category C itself. But then pick any algebra in C and take its modules. That's a natural set of examples. And then all good examples are essentially exhausted by this. And then there's some pathological special cases you can do that are not covered by this. But anything nice is recovered by categories of modules over algebras. And now we get to Frobenius algebras, and this is sort of the first time where so far the two tensor products have kind of been mirror images of each other, but they've kind of lived in separate worlds. And now we're being forced to honestly mix them because we want to do Frobenius algebras. So, and we get the following three characterizations of Frobenius algebras, which you probably are familiar with from other rigid tensor categories. So I'll go through them. So let A be a unit of a associative algebra and C with the white tensor product. So we have a multiplication from A tensor A to A, and a unit from 1 into A, satisfying the usual conditions that algebra will satisfy. And then we have a bijection of three types of structures. We have co-algebra structures, but these are now with respect to the black tensor product. So they get an A to A left exact tensor product A, and a co-unit from A to K, because K is the unit for black tensor product, such that this property holds. And you'll see this is exactly the same as it is normally for Frobenius algebras. It says that the co-product is supposed to be a homomorphism of modules, but normally you have to associate to re-bracket tensor products. But here we're mixing the two different tensor products, and so we can't use associators, we have to use these distributors to do that. So that's where they appear in the structures here. Then another characterization of Frobenius algebras is having a invariant form, bilinear form in the algebra. So one where you can have an object paired with a product, and then you can move the factor between the two arguments, which is what's written here. And the third is something called Frobenius forms, where the definition was a little bit too long to write out if it comes to the other slide. But these are closely related to basically whether or not A is isomorphic to its dual as a module. And so these are famously the three characterizations of the Frobenius algebra, and they hold naturally also in Grothendieck-Verdier categories. And so we could ask ourselves, can we find Frobenius algebras? And yes, we can. And I'm almost 5 minutes. Yeah, okay. So there exists something called a Serre functor or relative Serre functor, which allows us on these distinguished subcategories to identify internal Homs and internal co-Homs. And the Serre functor is when we restrict it to C as a modulo of itself, it is a monoidal equivalence between these two distinguished subcategories. And so it exchanges the white tensor product with the black tensor product. So in a sense, the two tensor products are identifiable on these subcategories. It is also a twisted module functor, and most importantly is if an object is sort of basically sent to itself under the Serre functor, so if it's sent to something that's isomorphic, then for any choice of isomorphism for identifying these two, we can construct a Frobenius structure on the internal end of N. And so this gives us a nice source of Frobenius algebras. Yeah, so this is it for the results. So we can summarize. So the main take-home point I'd like you to remember is Grothendieck-Verdier duality is a natural duality structure of many algebraic phenomena. So it covers associative algebras. It covers something like tangles and other more bizarre things. It was originally studied in the context of alternate models for logic, where you have two binary operations and or, so you've got the two tensor products, and the dualizing functor is negation. That's thinking. There is a natural theory of categories of module categories over Grothendieck-Verdier categories, which is the conclusion that we're talking about in this talk. And they provide many of the features needed for doing conformal field theory, which is what motivates me. And then, of course, the next step that we want to now do is actually do conformal field theory with Grothendieck-Verdier categories, which, yeah, is yet to be done. And so, thank you very much for coming.
So for constructing CFTs, do you envision using some kind of reference instruction? And do you
Sorry, can you say that?
for constructing CFTs, do you envision using some kind of reference instruction type of plane and just
Yes, exactly. Yeah, full talk construction. So I mean, this is a collaboration with the S of FRS. This is exactly our plan.
so is it sort of a part of that work?
No, nothing is worked out so well. So we've now gotten the module one categories under control, and there's also previous algebras. And so, yeah.
Could you go to the slide one, please?
Yeah. So, which slide number was it?
11.
11. Okay. Cool. 1, 2, 5. Yes.
Okay, so right, the whole point is that you don't quite have tools. You have this like weaker node.
Yeah.
But so it seems strange to us that under the image of modular functor, something which doesn't have a dual goes to something that does. This is
Under the image.
right. You can say that it has the image of C under the module functor considered as the module functor to any morphisms. Went from something that does not have a dual to something.
Yeah, we merely expect it to have the right adjoint.
Which is the same thing as the right dual in the node.
It's weaker, right? I mean, yeah, the full duals, the dual again has right adjoints. We merely want it to be right exactly right close. That's a strictly weaker property. So with duals, yeah, one of their properties is that you can form over the other side, but then you can. If the other side, you can also pull them back, and that still dualizes them. And the idea is there's a handedness to the direction. You can go that direction.
Yes. I guess they're just.
Yeah, we can discuss it later.
So one thing about the prevention of what you get in the end.
Yeah.
You get some endomorphism, not endomorphism, but something from M to F.
Yes.
So can I view this somehow as a generalization of the Handel endomorphism for the classical case?
And the generalization of which morphism?
The Handel endomorphism, like case.
I don't know. I haven't thought about that. Maybe we can discuss that more.
Oh, if there are more questions, let's finish it again.